Hi everybody, today we're going to start with Unit 1, Atomic Structure and Properties. As a reminder, please take handwritten notes. These can either be with a notebook and pencil on paper, or you can do it with a tablet. Regardless, I will be checking these notes at the start of the next class. These are some of our topics that we'll be covering in Unit 1. We'll start with moles and molar mass, go on to mass spectrometry, elemental compositions, composition of mixtures, atomic structure and electron configuration, photoelectron spectroscopy, periodic trends, and then end with valence electrons and ionic compounds. Some of this might be review for all of you, but regardless, we're going to go through this entire scheme and then move on to Unit 2. But first, we'll start with topic 1.1, moles and molar mass. Now, as a reminder, 1 mole is defined as 6.022 times 10 to the 23rd particles. Now, what do I mean by particles? Particles means really anything. These can be atoms, molecules, fish, if you want to think about it, grains of sand, whatever it may be. Now, a scenario that you would use Avogadro's number to convert between number of particles and moles would be in a question similar to this. Find the number of iron, or Fe, atoms in 15.0 grams of iron. What we do in this case is we would take our mass, 15.0 grams of iron, and then we would divide by the molar mass of iron. In this case, it is 55.845 grams of iron per 1 mole of iron. And for that, we get the answer 0.2686 moles of iron. Now you might notice that I have a little bit too many significant figures, but I will deal with that later on. And now to convert between the moles of iron and the number of atoms of iron, what we would do is take 0.2686 moles of iron and then use Avogadro's number to convert to the number of atoms. So 1 mole of iron is 6.022 times 10 to the 23rd atoms of iron. If you see here, our moles of iron cancel out with our moles of iron, and what we're left is with atoms of iron. And this is 1.6 times 10 to the 23rd atoms of iron. Now another concept with moles is the mole fraction. Mole fraction is defined, mole fraction is equal to the number of moles of X, whatever it may be that you're interested in, divided by the total number of moles in your sample, whether that be the amount of iron in iron oxide, for example, rust, or the amount of potassium in potassium chloride. Basically, the mole fraction is the number of moles of X divided by the total number of moles. Now, an example of how you would use this calculation is in a question such as this. Find the mole fraction of 18.0 grams of K2SO4, or potassium sulfate, dissolved in 150.0 grams of water. What you would do to start is take your K2SO4, 18.0 grams of K2SO4, and then multiply it by, or divide it by, the molar mass of K2SO4. In order to figure that out, what we need to do is add together the individual molar masses of all of the atoms in K2SO4. So it would be 2 times the molar mass of K, 1 times the molar mass of sulfur, and 4 times the molar mass of oxygen. And what we get when we do that is 174.26 grams of K2SO4 per 1 mole of K2SO4. Once again, grams cancel out with grams, and what we're left with is moles. And for this, we get 0.1033 moles of K2SO4. Now we can do the same thing for water, 150.0 grams of H2O. The molar mass of water is 18.0 grams of H2O per 1 mole of H2O, just about 18. Once again, grams and grams cancel out. We're left with 1 mole of water, and the answer to that is 8.326 moles of H2O. And now finally, to find the mole fraction, all we do is plug into the equation that I showed on the last side, which is moles of X divided by total moles, which in this case would be 0.1033 moles of K2SO4 divided by 8.326 moles of H2O plus 0.1033 moles of K2SO4. And our answer there, our mole fraction, once you do the math, is equal to 0.0122. And if we look back at our significant figures, we only have 3 because 18.0 has 3 significant figures, and you can see our answer here is in 3 sig figs. Now, a similar concept is the mass percent. And so in this case, instead of reporting with moles, what we do is the mass of X divided by the total mass times 100%, which would equal our mass percent. And so an example of where you would use mass percent is in a question similar to this one. A sample of lithium carbonate, Li2CO3, weighs 50.0 grams. Find the mass percent of lithium in the sample. The way you would approach this is take the mass that's given to you of lithium carbonate, 50.0 grams of Li2CO3, and then use the molar mass to convert to the number of moles of lithium carbonate. Molar mass of lithium carbonate is 73.89 grams Li2CO3 per 1 mole Li2CO3. And again, you get that by just adding up all the constituent parts of lithium carbonate to get the molar mass. And that would equal it would not. That would equal 0.677 moles of Li2CO3. Now using that, we can convert to moles of lithium, our actual constituent of choice. That's very simply done by multiplying 0.677 moles of lithium carbonate by the ratio of lithium to lithium carbonate. In this case, there's 1 mole of Li2CO3 per 1 mole of lithium. The way we know that is because in our lithium carbonate here, we have 2 parts lithium, meaning there are 2 moles of lithium per 1 mole of lithium carbonate. Once we do that, we get 1.353 moles of lithium. And then once again, using the molar mass, we can convert over to grams of lithium, which is what we're interested in. 1.353 moles of lithium times the molar mass. 1 mole lithium is 6.94 grams of lithium. Answer that you get there is 9.39 grams of lithium, and then we can plug this directly in our equation for mass percent. Mass of X over total mass times 100%. So in this case, it would be 9.39 grams of lithium divided by the total, which is 50 grams, 50.0 grams total times 100%. And the answer that we get here is 18.8%. And so the mass percent of lithium and lithium carbonate is 18.8%. That's all I have for today. Thanks, guys.